All right, everyone, welcome to the session. So we're going to start a bit late now, but we begin with Tim Möbus, who is going to talk about bosonic Hamiltonian learning via new information propagation bounds. So Tim, please, the floor is yours.
Okay, thank you very much for the introduction. Okay, so as Daniel already said, today I will talk about a project with Andreas Bluhm and Matthias Caro, who are at this conference as well and in the room as well, so he can support me or they can answer their questions, and also with Werner and Cambyse Rouzé. So okay, first of all. Oh, now it's working. Okay, first of all, I will talk a little bit about the motivation, so the task we are trying to solve here. And then I will give our bosonic algorithm which solves the problem. And then finally, I give some ideas which we use to construct the estimator in the somehow not working properly. I will give some ideas for which we use for the estimator in the algorithm or the protocol. And then at the end, I will give the final result. So let's start with the task we are trying to solve here. So we kind of have a black box, and we want to gather information from it. And the black box is a time evolution, and we have some product input states. As I said, it's a time evolution, so we can get a state back from this black box after some time t, which can be changed. And then at the end, we are allowed to measure the output state. And from this output state and the measurements, we get some data. And by post-processing, we want to learn about this box, about this time evolution. So we want to learn the coefficients of the Hamiltonian, which defines the time evolution. And of course, we also need some structure in the Hamiltonian. So we have a many-body system here. So we have, for example, nearest neighbors. And okay. So the task is to learn the defining coefficients in the Hamiltonian up to a position epsilon and under some probability assumptions. So, and these assumptions should be somehow physical. So, for example, we have access to the input state, the output state, the time it evolves.
Sorry, Tim, to interrupt you, but I think there are some connections with the projector. So maybe if you can just pause for 1 minute or so we can see if we can fix them. Oh, sorry about that. It's a view screen.
Let's try it.
Let's see if it wants to take minutes. Yeah, sorry for interruption, Tim. Please continue.
So, okay, shortly repeat. So we have some input, we have some black box, we have some output, we have a time we can adapt, and then we want to measure the output state, get some data. And from the data, we want to learn the coefficients which define the Hamiltonian. And now, it's called bosonic Hamiltonian learning. So we are in the continuous variable case or the bosonic system case, and want to learn the Hamiltonian or the coefficients. And of course, this is used, this is a very fundamental task. We have some device or some experiment, and we don't know really what's going on. We know some structure, but we want to learn this. And I mean, in many other talks, we've already seen the CAD code or GKP code, which, and there, for example, we can characterize those unitaries, and also the Bose-Hubbard model, for example. So, but before we look at the bosonic case, I will shortly recall the qubit as 2 qubit results, which are like very close to ours, but of course there are many others. But I just picked out those 2. One is about the standard quantum limit, which is also by Daniel et al. And the other one is the Heisenberg limit case, which is by Robert Hung et al. So there the task is that you have a qubit system, you have a Hamiltonian, or one of their results is that you have a Hamiltonian and this many qubit system, and you express the Hamiltonian by by Pauli matrices, more or less, in a Pauli basis, and now you want to learn the coefficients there. And the standard quantum limit result scales like this here. So you have the precision epsilon to the -2, and logarithmic in m, which is the system size, and delta, the underlying probability. So here's, I mean, one very important aspect is that you have only the system size logarithmically in m. So you kind of use the locality once assume like nearest neighbors, you assume on the Hamiltonian. In the case of the Heisenberg limit or the Heisenberg scaling, you have epsilon to the -1. So this is called Heisenberg scaling. But on the other side, you also have some like other parameters. For example, the time, the total or time you have to evolve the experiment is like epsilon -1 and logarithmically. And at the same time, you have to interact with the evolution in very short time steps. So the time resolution is quite high. There are also results showing that only under those assumptions you can achieve the Heisenberg limit. On the other side, the standard quantum limit, which is scaling not that good in the total evolution time. So you need to learn the Hamiltonian, the time you need to learn the Hamiltonian. But here, for example, the time you run the experiment is just a constant, and the resolution is fully logarithmically in epsilon -1. So the time steps after which you measure are much larger, which is like sometimes perhaps more physical, because perhaps your given experiment has a lower limit on those parameters. Okay, so and this is like the case we want to show for bosonic systems as well. Okay, so now in the bosonic system, we first choose a preparation as well here. So and this is the coherent state. So this is just because of some nice properties we will see later, but also because coherent states are kind of simple to prepare in these systems. Then we evolve the system by an Hamiltonian, for example, the Bose-Hubbard model. And now the task would be to learn those coefficients, right? And here we have maximal fixed time, but also some smaller time steps, which scale like polylogarithmically later in epsilon. And last but not least, we want to measure the output state by a heterodyne measurement, which is given here, locally defined. So it looks like a coherent state a little bit. It is a POVM, so it's really a measurement. If you integrate over beta, and beta is in the complex plane, then you get back the identity up to a scaling. Important here, it's now like the output, if we measure the probability distribution we get, is continuous. So the POVM is giving us a density function, and we have to take care later. So, okay, now the one property we want to use is the following. So the coherent states are eigenvectors of the annihilation operator. So we have this property. And by this one can show that if we apply the Hamiltonian onto the input state with respect to the measurement, the POVM, one can show that this looks like G, and G is a polynomial with prefactor. And the coefficients in this polynomial directly relate to the coefficients of the model, so like the Bose-Hubbard model. So the coefficients would be some related to lambda. Okay, but what we see in the experiment is not this G. So what we really can measure is this probability, or estimate this probability distribution. So now you see this is the evolved state, the measurement, this is our density, and if we could integrate over a region in okay, there's the square is too much in the complex plane, and here I'm restricting now to J. So the measurement here is locally defined and just on site. You can also do edges and so on, but in the sake of simplicity, I choose just on one side. And then you get the probability that your outcome is in this area B is given by this integral. So now for our algorithm, we choose, for example, this B beta, which is just the square until the point beta. And then, we could estimate this, but this is still not giving us the first equation, because then we have the derivative at 0, right? We have directly the Hamiltonian and not the evolved state. If we would just follow this path by a finite difference scheme, we wouldn't achieve the scaling we want, and this is already seen in was already seen in a qubit case. So what we do is some strategy similar to a qubit case, which is that we approximate this output probability function by a polynomial. First, by a Lie Robinson bound to have some local evolution. Then we tailor, so we get a polynomial. Again, up to some scaling, which we know, so it's not so important. And if we again differentiate in T and beta, we get back this G. And the G is kind of the information we need to get the coefficients. Okay, but now in practice again, we don't just get these probabilities here. We really need to sample. So what we do is we just check in this box whether there's a point or not. So this is kind of the estimator at the end. And by Hoeffding's inequality, this shows us that we can estimate those points here. So for different alpha, beta, and t's. And now for different alpha, betas, and t's, so beta is defined here, alpha the input state, t the time, we sample for different points, estimate these points, and then interpolate by a Chebyshev interpolation. So we get this polynomial. And now we know by this interpolation scheme that this polynomial is close to this polynomial, okay, up to this factor which we know. So we really know, okay, these polynomials are close to each other up to some epsilon we can control. And now we want to connect this polynomial to G, which is then done by Marcus-Brother inequality, which is showing us that if these two are close, we know that the derivative of this is close to the derivative of this. And this is what we want. But now we have a problem, because for these bosonic systems, Lie Robinson bound and Taylor expansion does not exist always. So if we just take the Bose-Hubbard model and try to Taylor expand, it's not converging. The problem is that the annihilation creation operators are unbound operators. If we, in a Taylor expansion, you have products of those, they just blow up the limit at the end. So it's not clear whether it's converging. So you shouldn't do this. Lie Robinson bound the same. So in general, Lie Robinson, and there are even counterexamples by Isaac et al. Showing that there are no existing Lie Robinson bounds, or model where you don't have existing Lie Robinson bounds. So, but there's hope by a result by Kuwahara et al. Showing that, for example, for the Bose-Hubbard model, you can show some Lie Robinson bound. And this is kind of our main technical contribution in this paper, that we are able to give an assumption which is more or less simple to show that there is a Lie Robinson bound. And the Lie Robinson bound look like this. So you have some Markov, some semigroup or some evolution, and you approximate by an evolution which is locally defined and a cutoff. So we cut off at some energy, and then it's a finite operator. So this is bounded. And for bounded operators, Taylor expansion, of course, converge. So for this operator, we can Taylor expand. And then by this Lie-Bromlin bound, we can use the strategy I explained before. So now this assumption, which I haven't written down here, is a little bit technical. For example, satisfied by the Bose-Hubbard model, any quadratic Hamiltonian in annihilation creation operator, or any polynomial defined Hamiltonian plus dissipation. The dissipation is this photon loss, which we know from the bosonic cut code, and there were already some talks about this. So if you add this dissipation to any polynomial Hamiltonian, you can enforce Lie-Bromlin bounds. So by this, you can kind of learn any Hamiltonian defined like this. But of course, for the cut code, somehow the dissipation comes in by definition or by the construction of the code. But if you just have a Hamiltonian lying around, more or less, you want to add this dissipation. And this, for example, we provide a throttle scheme here. So we intersect this evolution small time step by this dissipation to enforce it. But in general, you just need the assumption for our Lie-Bromlin bounds, and then you are safe to learn the Hamiltonian. Okay, so if you have this Lie-Bromlin bound, we can prove the following, which is exactly what we want to achieve. So we can estimate the coefficients in the Hamiltonians, so like the lambda, mu's, and u's in the Bose-Hubbard model, and then up to a precision epsilon with some underlying probability coming from the probabilistic nature of quantum physics, and we need the standard quantum limit, so the total evolution time epsilon -2, and logarithmically in the number of modes, so the system size. And then the maximal time we need is constant, and the resolution time, so the smaller time step we need for our interpolation scheme, is then polylogarithmically in epsilon -1. Okay, here I just want to remark another result which came out the same time as ours, which is about the Heisenberg scaling. So for the Bose-Hubbard model, there's also like another paper by Yu Tong giving the Heisenberg scaling with unfortunate resolution, which depends on the system size, but also achieving the Heisenberg limit. And okay, this results for the standard quantum limit. Okay, then, okay. Thank you for your attention, and feel free to ask questions.
All right, thanks, Tim. Do you have any questions from the audience? I think there's one down there. Yeah.
Yes, thank you for a nice talk. Perhaps an naive question, but what do you mean with a polynomially defined Hamiltonian?
Sorry. So it's kind of, okay, if we go, for example, back to the Bose-Hubbard model, it's kind of, I mean, the polynomial in AI, AJ. So we just, I mean, if you take a multivariate polynomial, and the inputs are more or less the annihilation creation operators defined on different modes. So this is a polynomial. And for example, the quadratic one, the Gaussians are somehow polynomials in annihilation creation operators.
I see. So basically, any Hamiltonian uses creation and annihilation operators that has any like efficient description is actually polynomially defined, then I guess. Or,
yeah, exactly. Yeah. Exactly. One needs to be a little bit careful, because if you go to higher power polynomials, it's not clear whether the Hamiltonian is always defined. So then another assumption that this Hamiltonian is kind of physical, so it's defined or well-defined is needed, but it's kind of, yeah, physical.
I see. Thanks.
Thanks for the talk. So I have one question for the estimated parameters that you obtain. So they are dependent on the energy that you fix from. So somehow you can, if you take the limit, if you want the full energy limit, so how it behaves, does it affect a lot or not?
I mean, somehow in another assumption which I skipped is that, I mean, okay, not really skipped. These coefficients are somehow bounded, so the absolute value is like finite. So if I scale this to infinity, of course, the bounds would blow up. and the energy I cut off is more like a mathematical tool during proof. So this cutoff I mentioned shortly in our Lie Robinson bound. So this one is chosen in the proof more or less. So this M is more or less fixed, that we know, okay, it's approximating well. But I mean, I could also write down the Lie Robinson bound without the M. So then there's still a Lie Robinson bound. It would more be a problem for the Taylor expansion, but it's kind of a trade-off at the end. But like, I mean, for the fixed preparation for fixed like coefficients, there's no energy constraint.
Thanks.
So, okay, the first question is, your results holds just for Bose-Hubbard Hamiltonian or also for more general Hamiltonian?
I mean, for any quadratic Hamiltonian. And I mean, if you add dissipation, you can do any polynomial.
Okay,
So
and M is the number of modes, right?
Exactly.
Okay.
M is the number of modes, so it's somehow the system size.
Okay, and I would expect that the total time required on your final result will depend on also on the total number of coefficients that you have to learn, right?
Yeah, exactly.
Why that this?
I mean, it's kind of, I mean, if you, for example, assume to be nearest neighbor, which is the case for the Bose-Hubbard and you're on the lattice, for example, I mean, then it's like the system size. It's dependent on the system size, like logarithmically in M. This is where the logarithmically in M comes in. So of course, if you now do like K local, I mean, we're doing Lie Robinson bound for K local Hamiltonian, but not the learning, but we expect it works in the same way. Then it would depend on locality. Of course, if you have now very, very large K local Hamiltonians that defined in large regions, this depend on this region. And yeah, okay, but the system size coming in here is only this logarithmically M. There's no number of terms coming up with it. I mean, in the post-processing task, of course, you have to calculate all the data, but for the measurement, you do some parallel schemes to have this logarithmically M.
Okay, I see. Thank you.
Yeah, you're welcome.
Okay, I think we have time for one more question. Are there any questions? Oh, if not, then I can ask one. So you mentioned these works that achieve a Heisenberg scaling, but as far as I know, they all only can do like closed system evolutions. They cannot, let's say, learn dissipation, the dissipative terms as well with Heisenberg scaling. Do you think that's possible, or like
for the Heisenberg or for ours?
Yeah, like get a Heisenberg scaling and allow for dissipative terms in your evolution?
Yeah, I'm not sure. I mean, we're working on something using dissipation to achieve the Heisenberg scaling without. I mean, I mentioned shortly the result by Yu Tong, where okay, first I go back to the qubit case. So I mean, the bosonic learning result for the Heisenberg scaling has an M here, which is like system size dependent, and by some using dissipation, you can erase this M there, that you have somehow a similar result for the qubit case. But I'm not sure about Heisenberg scaling for Lindbladians. I mean, about our scheme, I think it should work. It's more like tedious to do it, but should work. But because we also have Lie Robinson bound in for the Lindbladians and stuff like this.
Thanks. So yeah, let's thank Tim again, and I guess now we take a 5-minute break while the next speaker sets up, and we'll continue at 11:05.
That is shortcut for
You Control L. That's not working.
Hello? Yeah.
All right, welcome back, everyone. So now we have the second talk of this session. So we'll have Samuel talking about conditional independence of 1D Gibbs states with applications to efficient learning. So Samuel, please, the floor is yours.
Thanks for the introduction, and also thanks to the organizers for having me here. This is joint work with Paul, Alberto, Alvaro, and Angela. Before I want to talk about conditional independence of 1D Gibbs states and learning, I just start with like something kind of off topic, which in my view kind of motivates this work, namely gap ground states in 1D. Ground states in 1D are something that's computationally very hard, but it has been found a while ago that if you assume a gap on ground states in 1D, then you can prove something about them, namely that they have an area law for the Renyi entanglement entropy. If you don't know what that is exactly, I'm not going to explain it, it's not important for the talk. The result by Hastings a while ago. And from this result, which is like an information theoretic criterion on these gap ground states, it has been proven that they have efficient matrix product set representation. So some kind of compressed tensor network description of these gapped ground states. In 2006 by Westrate and Sirac, and later on this has been extended. They don't only exist, you can also find them. So they are efficient algorithms proven a bit later. And I like this kind of story of you start with some physical assumption, namely the gap on the ground states and the setting. You prove something about information theory on these states, which is a more general criterion. So now you can well, first of all, it's just an information theoretic result. And later on, when you say this implies efficient algorithms, you could also potentially extend it. I mean, in this case, it's not true because they're actually all equivalent. But potentially, if you know this information theoretic criterion, you can just check it and get this algorithmic efficiency afterwards. So this is the side story. And in this talk, we talk about 1D Gibbs states. And as you might guess, I want a similar story. And that's not how it has been proven. So for 1D Gibbs states, these tensor network representations have been found. They're mostly explicit constructions, but part of the motivation of this work was, can we still, despite the different proof, reproduce this story? So can we start from these 1D Gibbs states as a physics assumption, find some information theoretic criterion yet to be determined. Spoiler, it's going to be something with conditional independence, conditional mutual information. You saw it earlier in the plenary talk. And then use this information, like this information theoretic criterion, to go at least to an efficient MPO representation. And it turned out we can. This is kind of the outline of the talk. And as sort of the corollary of the whole work, it was like the additional application is that we can also learn this representation. Okay, just one boring slide with a little bit of notation. And we talk about 1D Gibbs states. You think of a chain of spins. Each of them is a finite dimensional Hilbert space. And we define a potential function which maps each subset of the chain to a Hamiltonian term supported on this subset. Think of these as the Hamiltonian terms. Mostly they will be finite range, but in fact our results extend to those being exponentially decaying. So the norm of these terms decays with the system size of this x. I will always, for the moment, put my chain in 3 pieces, which is why I always have the sub-indices ABC. And you always have a Hamiltonian which consists of all terms that are supported in the subset ABC. Our terms will also always be translation invariant. The inverse temperature is beta, and then we define the Gibbs state, which is the inverse exponential of this Hamiltonian divided by some normalizing factor. Sometimes we'll talk about margins as well. So if there are subscripts instead of superscripts, these will be local marginals of this Gibbs state. I will come to this later. Okay, so conditional independence, as I said, is the thing that we want to prove. There are several notions of correlations in 1D Gibbs states. You could talk about decay of correlations, about mutual informations, but we care about conditional independence. And this is characterized by the conditional mutual information, which in the standard version is given by this formula. So you take a difference of some entropies, or you can also see it as the amount of slack in the strong subadditivity, which is the decrease of a relative entropy of rho ABC to rho A tensor rho BC when you take the channel being the trace on C. So if you remove this system, how does this quantity decrease? And this is something that characterizes quantum Markov chains. So as soon as this quantity is 0, it's possible to take a map from B and reconstruct this rho ABC by just the information in B in the state on rho AB. Yeah, this is when they're exact, and there's also an approximate version of this given by Fauzi Renner. In addition, it also has like other nice interpretations. You can give a structure result. And so overall, this quantity is quite well motivated. What we do is we use a different one. The one we use is basically takes the definition from the previous slide, but replace the relative entropy by the so-called Belafkin-Stastevsky relative entropy, which is a different generalization of the standard classical one. So if these operators commute, you can just take them apart, and this first line is just the same as the Kullbach-Leibler divergence or the Omegaki. But as they don't, this is in general a different quantity, There's kind of a literature in information theory about how to motivate this. It is a different generalization, so it extends the classical case, but still it's not 100% clear why in this context this is the right quantity to look at. Our motivation is just that we have results for it and an application. So kind of one motivation for it is just what I'm going to tell you later on. Also, one warning on this slide, I'm going to mess around with this definition a bit. It's possible, there are a few different equivalent definitions of the for Neumann CMA. You can, for example, put identities here instead of the row A's. We're going to switch them around a bit. The results hold for all of them. So whenever I exchange some of these quantities, don't worry, the decay results that we're going to achieve are all going to hold for all of them. But they might be inequivalent in the setting of the Belafkin-Sostevsky. Okay, so similar to this, what I just said about approximate Markov chains, there's a similar analogous thing for these Belafkin-Sostevsky relative entropies. So if you have these sort of channels, so this data processing inequality that this quantity is greater equal 0, because a channel or a bunch of maps only decreases this quantity, then if it's 0, you can recover with one map this state sigma from E of sigma, and the same map also recovers rho from E of rho. This is a bit more general than what we had before, but later on we will pick this channel being the trace on the C system. And the interesting thing that we want to first ask is this also an approximate equivalence? So we will first just go in the right to left direction. So if this recovery condition is approximately fulfilled, do we still have approximately 0 Belafkin-Sostevsky conditional mutual information once we plug in all the correct channels? And we find such a bound. So this is one of these versions of the Belafkin-Sostevsky conditional mutual information. And it's a bit hidden, but if you look at this thing here, this is 0 exactly when this channel, this recovery map exactly recovers our state. So this is a quantity which we want to upper bound. We think that this should go to 0 if the recovery map does a good job. And here are a bunch of prefactors which look slightly scary, but later on we will find out why we don't have to worry about all of them. Yeah, so the trick behind this, I'm not going to go into the proof, but just roughly, it's basically a long computation including a lot of Hölder inequalities and an integral representation of the logarithm. But just like this is one side of the result, you first relate this conditional mutual information, this entropy quantity, to these recovery maps. And in the second step, you want to basically just prove that all these, like these factors in the previous slide, are either bounded or decay. And for this, I just want to briefly introduce one technique that's interesting for this, for 1D Gibbs states in general, which is Araki expansionals. You take sort of something that looks like the Gibbs state, here just unnormalized, on two systems, X and Y, neighboring, and you compare it to the inverses of the Gibbs states on X and the Gibbs state on Y. We're just currently ignoring some partition functions. And the idea is, okay, if this is a commuting Hamiltonian, then clearly all these Hamiltonian terms cancel except the one that goes from X to Y, so it would be strictly local. And the result from Araki, which basically has been proven a while ago, basically you have this operator, instead of being strictly local and bounded, it's still bounded, but it's quasi-local. So if you take a slightly bigger region, you can approximate it very well. And in fact, this approximation is super exponentially good in the distance you take around the cut between X and Y. And basically, like a long list of lemmas proves that this ingredient is basically what you need to bound all these three factors and to prove that this factor decays super exponentially fast, which gives us our first result. This is information theoretic result on the Gibbs state. So this was like first implication I showed in my original motivation. You have some kind of scary exponential blow up here. However, you find a super exponentially decaying function. So as you take this tripartition ABC and you make the B system larger, the conditional mutual information decays very fast. And if you go to, this was for finite range interactions, and as I mentioned, we also have exponentially decaying interaction. In that case, the decay is only exponential, and it only holds above a critical temperature, which is kind of in line with all results we have for 1D Gibbs states. So it's basically nothing that doesn't break down below a critical temperature for 1D Gibbs states with exponentially decaying interactions. Okay. I already talked about some kind of recovery map. We found there are several ways of arranging these recovery maps, and you can get slightly different conditional image informations with slightly different recovery maps. And there's another one which looks a bit more complicated than the previous one. It does not have anymore, as the previous one, trace preservingness, but it is opposed to the previous one, it's completely positive. So you have like a factor here, and it's adjoint on this side, so you clearly see this is a completely positive map. And it's another version of a recovery map for the BS relative entropy. Namely, if you take this channel and you try to reconstruct, okay, this time I went the other direction, but if you try to reconstruct the A system of a chain by a channel just acting on the B system, like from B to AB, and ignoring the C part, you can reconstruct row ABC from row BC. And so there's an upper bound. If the CMI here, slightly different version again, as I warned you. If the CMI is small, then the recovery channel is good. Again, we will find separate bounds for these prefactors here. So this was just, one recovery. But what we want to do is we want to find this tensor network representation. So we want to break up this chain into small matrices, and these matrices will actually be the recovery maps. So what we do is we make like a chunking. So we take little chunks that are sufficiently large that from our first result, the conditional image informations that we are interested in are already very small. And then we take the state on A1, reproduce the state on A2 by acting on A1, reproduce A3 by just acting on A2 and ignoring A1, and so on and so forth. So you have this chain of recovery maps that is a good approximation of the full thermal state on the N subsystems. And as I said, what I want is I want a sufficient criterion for the existence of such a tensor network representation or recovery map chain reconstruction. And we have sort of, we try to write everything as an information theoretic quantities, everything as an entropy. And this is the one we talked about before. So we have a decay result for this one. It has been previously proven that this one, the max mutual information, is actually has an area law, so it's uniformly bounded. And for this one, we have the result also somewhere hidden in our paper that these two factors are uniformly bounded, and this gives us a decay for Gibbs states. So you have a more general criterion, but for Gibbs states, it's fulfilled. So for Gibbs states, we get an efficient approximation. With this chain of recovery maps. Again, this is like intrinsically a positive decomposition. That's not always true for a tensor network representation. But since we use these completely positive recovery maps, it's kind of a nice little extra that this comes for free. Okay. Finally, as we advertise, we also talk about learning. The learning is kind of straightforward. So once you look at this map, it's completely positive. What does it actually consist of? It just consists of all these marginals. So the idea behind the learning is just, well, since these are all things, we just do local tomography. Each of the system sizes isn't too big, so we just basically throw any standard tomography results on all these factors. Because it's an explicit formula in terms of marginals, and we use just like standard tomography on the system sizes. The system sizes are less than log large. So we get, each of them can be learned polynomial time in inverse error, and in the global system size, because the global system size does not enter into the size of these marginals. And you get a bound on the bond dimension, which is basically given by the size of these recovery maps, and a runtime bound on the sample complexity and time complexity of the learning. Okay, so this is already where I come to the conclusion, just to like wrap up the steps that we had before. We prove this super exponential decay of a certain form of BS conditional mutual informations. There are two steps involved. One is just like we go from this quantity to a data processing quality with these recovery maps. And then in the second step, once we have these recovery maps, we use this technique that is kind of crucial for most results in 1D Gibbs states, which are these hierarchy expansionals. What's new is this recovery map was actually known before, but we also introduced a new recovery map, which is kind of the opposite side of the data processing inequality. It's a strengthened data processing inequality, which allows us to give this tensor network construction. So we have like a result on how well this recovery map reconstructs systems with a small BS conditional mutual information. Chaining those maps together gives us our MPO reconstructions, which we then can also learn by just measuring marginals. a thing that I didn't quite pack into these slides, but it's sort of similar techniques than the one we used, allow us to also learn the purity, so the trace of the squared thermal state, which is kind of a different result on something that's sometimes compared to entropy. It's related to the 2-Rényi entropy of the global state, and it's in general hard to learn. But with a similar factorization trick, we can also learn the purity. But I'm skipping the details for this one. Feel free to ask questions or look at our paper if you're interested. And finally, I want to comment on something related, since after we published our results, we found that, or there was a result as well on the von Neumann conditional mutual information, how it decays. So you could ask, this was kind of the original quantities that was more, well, better known, probably also better motivated than the BS conditional mutual information. The question is, can you do similar things? And the answer is mostly yes. On the one hand, one sort of thing is, I mean, I say weaker result here, but it's still a really good result, which is the exponential decay of the conditional mutual information, but it does not extend to the slightly stronger super exponential decay, and it's not known to hold for exponentially decaying interactions, where you have this high temperature result for the exponentially decaying interactions. So there's like a tiny difference in the extent of these results, but still you have the decay of the standard conditional mutual information. And then the question is, could you do an analogous construction for these MPOs? And the answer is also yes. In general, you can use so-called rotated Petz recovery maps. You have to use rotated Petz recovery maps because the standard ones only work in the exact setting, but the rotated ones would work similar to ours. I haven't looked into the learning. I presume it would be similarly possible. You have to get into the details whether all these error propagation bounds from approximate marginals still go through. But this would be an alternative route now, since this result also exists. This is just a comment on the comparison to something that came up afterwards, and we, but still we still have some settings in which our results sort of are not covered by this. All right, and that's the end of my talk, and thank you for your attention.
Thanks, Samuel, for the great talk. Do you have questions? Yes.
So I didn't get, what is the temperature bound here? I mean, it doesn't hold for...
It holds for all temperatures. The temperature dependence is bad, but it holds for all temperatures. Doesn't break.
The what, sorry?
The temperature dependence should be...
When beta goes to infinity, do you still have an area law? You surely don't have an area law.
You will still have decay of conditional mutual information. An area law should break down, yeah.
Okay, but then it should...
So no, an area law actually also holds. In 1D, an area law also holds at arbitrary high temperature.
No. I mean, you have QMA hard things. I mean, I don't think you have...
So
I mean, you have a ground state.
The bounds get very bad with the temperature, but they have no critical temperature where they break actually down.
But then you should not expect an area law in that case, right? You should not expect an area law and nor an efficient MPO representation for the ground state. I mean, it's a
fixed arbitrary temperature.
Yeah, okay. But then it becomes temperature dependence should go in there and makes the bound worse and worse.
Yeah, yeah. But at a fixed temperature, you can still do it.
Oh, yeah.
It should be the dependence, I think, is doubly or triply exponential in beta. So it's absolutely not great. But as soon as you fix it, you can still do it at any temperature.
Thanks again for the talk. You assume that the underlying state can be written as an MPO, or do you also have to do some truncation? And
so there were known results on that you can write it efficiently as an MPO before, but the construction we use, we actually prove on the go sort of that it is an efficient representation. So the construction is exactly this. And this is part of our proof that this is an efficient MPO representation.
Like there's an exact finite bond dimension for the Gibbs state. Like there's no...
Well, so sort of, okay, it's not exactly, there's an approximation in the tensor, but we don't afterwards truncate the bond dimension. The bond dimensions that comes out of this construction is already polynomial in system size and the error that you want on this side.
Okay.
Okay, sorry. Thank you very much for the talk. Just a question about the translation invariance. Can you relax that Maybe actually a follow-up also. Is there anything known about trees?
Regarding translation invariance, so far I have no idea, because these results that we use, and as I already mentioned, these results are not exactly novel, so they have been around for a while, and no one has managed so far to extend to non-translation invariant. So I would say it's definitely at least very hard. For trees, kind of similar answer. This is just the technique that's definitely crucial to what we do. So I can't tell you about trees either.
Please.
Okay, thanks for the talk. So first question, is it to think about possible extension to 2 dimensions? So is it a relevant question to think about, I would say?
It's a relevant question. Okay, one answer is the same as to the previous question. This thing is just 1D. Second answer is things have to be harder in 2D. There are no phase transitions in 1D, but there will be in 2D. And maybe a third answer is it's very unclear how to do these chain recoveries. If you go on a 2D lattice and you try to like construct patch by patch your thermal state and use recovery maps to construct it, then as you grow the size that you've already recovered, the boundary grows as well. So such an idea of like, chaining recovery maps is very complicated and should actually not work in higher dimensions usually. And
another question. So for the EPO construction that you have, what are, I don't know, possible physical application? Like, I don't know, for example, for MPS, you have classification of phases of matter. You have different things. So for the MPOs, what could be possible physical application, I would say?
Okay, if you say classification of phases of matter, there are no phase transitions, so there's nothing to classify in that sense. One interesting thing, maybe to mention that this is not possible, is this is not a channel what we have. So these are recovery maps, might have misused the word at some point, but these are recovery maps, no channels. So one thing you could think of is like Gibbs sampling by just actually applying these channels. This is not possible since these are CP maps. If you want to make them into trace preserving, you kind of have to scale them down and will end up with a probability of failure in each step. So you get like an exponentially suppressed probability of actually managing to construct your state. However, I think this is something that would be possible if you use the von Neumann instead. So that's a downside of our result. We don't have an actual physical channel in this MPO reconstruction. So it's just, you should see it as just a numerical technique.
Thanks.
Well, we actually have time for one more question, so I want to ask a question. So you mentioned learning of purity. The purity will typically be exponentially small. So what's the figure of merit you're using to recover? Is like log of the purity, or?
We wrote down the purity, but it would be a multiplicative approximation.
Multiplicative approximation. Okay, thanks. All right, then if there are no further questions, let's thank Samuel again. And yeah, we have another 5-minute break and continue at 11:35.
Weiß nicht, was das ist. Sehr entspannt.
Eine Minute.
Okay.
Eine Minute.
Stelle ich mich wieder aus.
Oops. All right. Welcome back to the last talk of this session. Please take your seats. So, the last speaker of the session is Andreas Bluhm, who's going to talk about Hamiltonian property testing. So, Andreas, please, the floor is yours.
Okay. Well, this is joint work, as you can see, with Matthias, who has indirectly featured already several times in the session. He's sitting somewhere in the back with a mask, so you might not recognize him. And with Aadil who could unfortunately not make it, but who's the guy who actually did the work. So if you're unhappy with my presentation, if you have questions, just write an email to Aadil. He can probably answer better than I can. Anyway, so what are we trying to do? Well, we're in a similar setting as the talks before. I guess this is why we're in the same session. So we all know that quantum systems are governed by the Hamiltonians. This is why we care about them. And as Tim, for example, presented, sometimes we want to learn them from access to the time evolution. So this is actually borrowed from Tim's talk. So usually you have a preparation, you have a quantum system that you want to learn, you have kind of control its time evolution, but just switching it on and off at a convenient time. And in the end, you measure something. But what happens if we actually don't want to learn the quantum system? Maybe this is too much. We care only about like one single property, for example, whether the system is local or not. Of course, if we could learn it first, then we could look at it and say, look, I mean, it's local or it isn't. But maybe it's easier if you just want to know this property. So the question is this an easier problem or not? And well, this talk will give the answer to that in some sense. So what's our setup? So we want to consider a system of n qubits, so that's dimension 2 to the n. So far, so good. And since we're talking about qubits, it will be very convenient to do the standard thing, namely to take the Hamiltonian and to always write it down as an expansion in terms of Pauli strings. So these p's here are just strings of Paulis where each entry is like either identity x, y, or z. So from this set here. And these coefficients alpha p are just numbers. They're real numbers. And this is what you would, for example, like to learn if you do learning. So if you do learning, for example, you would want your algorithm to output an estimator h hat or alpha hat, depending on how you do this, such that some norm that you have chosen, I mean, this is your figure of merit, this comes with the problem, that the distance of the estimator to the actual Hamiltonian is at most epsilon, with probability, say, at least 2/3. Right? So this is the standard learning. This is not what we're doing. And often a learning algorithm would assume to begin with, for example, that the Hamiltonian they want to learn is local, and then you can show that then it's like an efficient algorithm. That's like a very standard assumption. But we basically, at the beginning of this project, we've thought to ourselves, well, how do people know, right? I mean, how do you know that you're local and can actually do this? So this is basically where we come in. So what do we want to do? Well, first we have to talk about locality. So I think like depending on the community, like sometimes this is also called k-bodiness. So like k-local for us means that basically all the coefficients alpha p here are 0, that for the p's that weight at least k. So that means that there's at least k, like more than k factors or entries that are not the identity. Just to check, for example, if you look at x, I, x, this is 2 local because there's 2 things that are not the identity. And x, y, z, x would be 4 local because there's 4 things that are not the identity, right? Good. So what's the problem that we want to solve? That's the following. So you're given a locality parameter k, so that's your locality. You're given a norm, anything, and an accuracy parameter epsilon between 0 and 1, such that, and then the Hamiltonian k locality testing problem that we write like this. So like if the norm, if the epsilon is the following task. So you're given access to the time evolution according to an unknown Hamiltonian h, as in learning, and you want to decide with success probability at least 2/3 whether one of the 2 following things is true, whether either h is k local or whether h is epsilon far from being k local in the norm that comes with the problem. So meaning that the difference to any k local Hamiltonian in this norm is at least epsilon. And if, of course, like it could be that h satisfies neither 1 or 2, and then you don't care, like any output is fine. So like if you're like a computer scientist, this is a promise problem. You sort of promised that one of the 2 things is true, and if the promise doesn't hold, then whatever. So of course, like instead of 2/3, I could just put any number that is larger than 1/2, at least it's constant, that doesn't really matter. It's just for concreteness. Right. So we know what the problem is. So now I have to tell you what we are allowed to do to solve it. And you could think about different settings. So for example, you could talk about these kind of strategies. So like each blue box is like one time you sort of like run a sub-step of the algorithm. And what you do is you prepare the state on a potentially larger system. So there might be ancilla qubits around. Then you run the time evolution, which is this red box there. on like the n qubits, then you measure on everything you have, and then you record the outcome. And you use the outcome in two ways. So once you put the outcome to the algorithm that in the end will tell you whether either yes or no you're local, and you can use it for the next round, right? I mean, so you can, for example, base your preparation and your measurements now on the outcome of the previous thing. And you can do this like for any of the previous outcomes. So this is why it's an incoherent strategy, because it always measures at the end of each step, and it's adaptive potentially, like if you use all the outcomes here. Contrary to that, we could look at coherent strategies. So that's a bit different. So there you just prepare one state, and again, like on potentially like an ancilla system, and you run the time evolution, and then you can use arbitrary quantum channels in between. Like these NIs are just like quantum channels, and then you run the time evolution again, you channel again, and in the end you measure, right? So like this is more powerful than that, because like, for example, you could use this ancilla system to just record your classical outcomes and then base your decisions on them. Right, so now we come to our first result. We have now set the stage for what we actually can do. And the first result is that actually this is not easy. Like depending on what your norm is, this might be hard. So if you take k at most order n, and you take any ancilla free, meaning that you do not have an ancilla, incoherent adaptive quantum algorithm, so that was like the algorithm on the left, but without ancillas, that solves the k-locality testing problem, even if you additionally guarantee that the unknown Hamiltonian is trace-free and that it is normalized to have operator norm at most 1. Even then, this algorithm has to make at least 2 to the n queries to the unknown Hamiltonian, and it has to use an expected total time evolution of 2 to the n divided by epsilon, meaning that you cannot actually do this, right? With an incoherent, maybe adaptive algorithm that is ancilla-free, solving this problem in the infinity norm, so like this, the norm that we approximate in, is not really feasible. Now you can ask, okay, like what about coherent algorithm? I mean, they are more powerful. Maybe with coherence, I mean, we're all doing quantum information. Coherence is great. This will surely work. But that's not true. So like even any coherent quantum algorithm achieving the same has to make at least 2 to the n half many queries, and it has to use a total evolution time of at least 2 to the square root of n, 2 to the n half divided by epsilon. So this is a bit better, but not much. So this is not what you want. So like, and also like this result actually, because the shuttle norm is basically the best case, that rules out testing in any p norm. And that's not something that you want. So now you can ask yourself, like, I mean, why am I even talking to you? I mean, if this is basically the end of the story, I mean, that's not very impressive. Well, at least the proof is interesting, and we will come to more positive things later on. So the proof goes as following. So you want to identify a distinguishing problem that a successfully local tester must be able to solve. And the way you do it is you construct a promise problem again in a random way. So like either the Hamiltonian is 0, or the Hamiltonian has like some random unitary, and you have to subtract the identity over D to make it trace-free. And you scale it by epsilon to make things like close together. And if you do this, then you can use like a concentration of measure argument for the Haar measure to show that in the case 2 here, epsilon is far from k local. So I mean, of course, like if h is 0, then it's very, very local because it doesn't have any terms basically. And the other one's far from being k local. So that's good. So that like a successful tester has to distinguish. And then we can use like standard stuff like Lecam's method to argue that the outcome distributions in the 2 cases also have to have a total variation distance. Then you can substitute the total variation distance using Pinsker's inequality by Kullback-Leibler divergence, because that's nicer to work with in this case. And then you have to sort of bound that. And you can use this like using Taylor expansion, Weingarten calculus, and all of that. So this is the main work that goes into this once you have the idea how to do it in the first place. Right. As I said, let's now come to more positive results. So like we have seen, Schatten p norms are bad. Yes?
What's the point when you're claiming that the distribution you get from this Hamiltonian is 0 Hamiltonian?
Yes. Yeah, that's exactly that. I mean, like sort of all the Hamiltonians have look very similar, and their distributions is why you cannot really distinguish them. So like if you could distinguish them, then you also would need to distinguish these probability distributions, which is difficult. That's the idea.
And what distribution are you looking at?
Basically the distribution of the outcomes, right? So like if you look at the outcomes here
for arbitrary channels
in this setting here. So I mean there's no channels here, right? I mean it's just like if you choose some measurements and you choose some state preparations which are not specified, then you look at the outcomes, and a tester for this problem then would have this distribution. Right. Thanks. Good. So as I said, like testing Schatten p-norms is not good, but it's hard. But we can choose a different norm, and we will choose a slightly unusual one, which is the normalized Frobenius norm. So like you take the Schatten 2 norm, but you divide by 1 over square root of dimension. So where the Frobenius norm is defined in the usual sense. And then actually we can think about what this means. And if you think a bit more about this, then you will find that this norm is basically the average case setting, whereas the operator norm corresponds to the worst case. So we have chances of that this actually works better. And this is the case. So again, if you take k at most linear, then if you again promise that the unknown Hamiltonian is trace-free and is norm at most 1, then there is an ancilla-free, incoherent, non-adaptive quantum algorithm. So like as easy as possible, you don't have to do anything fancy. That solves the Hamiltonian k-localities testing problem. And it only needs epsilon to the -4 many queries in the unknown Hamiltonian. So this is not a type where there's no n, there's no size dependence here. And it also needs a total evolution time of only like epsilon to the -3. So this is likewise size independent. What is not size independent is the classical post-processing time that you need in the end, which is n to the k+3 divided by epsilon to the 4. So this is where the size matters, but it's still polynomial in n. So this is something you can actually do. And it's only the classical post-processing time, right? So classical computers are easier than quantum stuff. And which is also nice, the testing algorithm also only uses stabilizer states as inputs and stabilizer basis measurements as measurements. So this is also easy for the quantum computer to do. So what does this algorithm look like? Well, so first we have to construct the states and measurements that we want to do. And you just take d+1 stabilizer basis from maximally abelian subgroups of the Pauli group. So this is like, for example, how you construct like mutually unbiased basis of stabilizer states. So this is fairly well known. And what interests us is not so much like applications in error correction, but like that a quantum computer can prepare and measure them efficiently. So that's why we like them. And then the algorithm is the following. So first you choose two indices I and j, uniformly at random, and prepare the corresponding state phi ij. Then you let the whole thing evolve under the unknown Hamiltonian for time t of order epsilon. And you perform a measurement in the same basis that you chose the state from, and observe an outcome L. And then you have to repeat this procedure n times. And now comes the sort of the important step. So now you look at all the L's that you recorded in stage 3, right? And at least one of them is such that if you look at the state where you started from and you look at the state where you measured, and sort of the transition from the start to the end cannot be explained by any k-local Pauli string, then something non-local has happened, and you conclude that you are epsilon far from k-local. That's the thing, because like this thing can either be 0 or 1. And otherwise, like if this can be explained by local stuff, then we claim that the Hamiltonian is H-local, because we have tried this often enough that when we haven't seen any non-locality, so it's probably not non-local. Right. So that's the algorithm, and then you have to prove that it works. And so like the checks in the last step, so these things are where the classical overhead comes from. Right. So let's for the proof idea, let's just take a sketch like for a simplified thing. So for example, we only assume that now we have only I or X, so like that's the commuting Hamiltonian. And for this thing, we can make our life a bit easier. This just like, I mean, the proof is actually more complicated. It's just like for the purpose of this presentation. So if you take 0 as the input state and a computational basis measurement, so we don't have to use this full algorithm. And then we notice that if you look at a string of x's, where j is a vector, then you can prepare like state j by just applying x to 0. And if you have short time, then you can approximate the exponential by linear term. So if you do that, then, for example, if you look at any n-bit string j with positive weight, then it holds that the transition matrix squared is basically of order like t squared times the coefficient. And now, if you assume that h is indeed k-local, then all of the alphas are 0 with too large weight. And now you can think about these things. So the probability of measuring anything that is high weight, right? I mean, I only look at the high weight things. Since these things are 0, those things will be 0. So like the whole thing is about 0. So like you don't make an error here. So like if you're in the k-local case, you will never see anything that will tell you you're not local. That's good. And conversely, if h is epsilon far from any such local Hamiltonian, then you can, by the choice of the norm, the sum of the coefficients squared will basically be larger or equal than epsilon squared, meaning that the whole thing, like the whole probability of seeing an outcome that tells you that you're not local is of order t squared epsilon squared. And then you only have to choose the t accordingly that this becomes constant. So like you have to repeat this whole thing like t to the minus 2 epsilon to the minus 2 times to make it constant. The t has to be small for this approximation to make sense, and this is what gives you what I showed you in the beginning. Great. And to make the proof precise, we have to deal with higher order terms and non-commutative stuff and so on. So this brings us to the last result. So the last result that I have is, now you could say, for example, I mean, we're still trying to solve the question, is learning actually harder or not than testing, right? So it could be that for this strange norm, learning is also easy, but this turns out not to be the case, because any even coherent quantum algorithm with a constant number of ancilla qubits or auxiliary qubits, when given evolution access to an arbitrary n-qubit Hamiltonian H, which fulfills like trace free and norm bounded, that succeeds with success probability 2/3 and outputs a classical description H hat such that you are close in normalized 2 distance. So any algorithm that actually solves the learning problem, that has to make at least 2 to the 2 n many queries to H. And if you restrict yourself to non-adaptive incoherent quantum algorithms, you get like 2 to the 2 n divided by epsilon. So this says that learning in some sense is still hard for this problem, if you don't make like the locality assumption, right? The point is that this learner has to not use the fact that that's looking at a k-local model, because you don't know that, right? And I think in the interest of time, let me shorten the proof idea a bit. So basically, the idea is the same. You want to identify a distinguishing problem that a successful general Hamiltonian learner can solve. You do it in a probabilistic way by taking unitary Cux that you apply to a fixed operator that is like half plus 1 and half minus 1, such as trace 0. And you also take them to be H-random, use concentration of measure to have a lot of Hamiltonians that look the same. So you can construct a family which is well together, and then you can use, for example, Farnus inequality that will tell you that the mutual information between the label of the Hamiltonian you're looking at and the thing that the learner guessed, that this has to be big, because this family was double exponentially big, so this is still exponential. And then basically you have to bound this mutual information from above in terms of the dimension of the systems involved. Yeah, so let's skip the rest. And so what I didn't tell you, I mean, I only told you about locality, but actually we can do a lot more. So we can actually also test any other property, meaning that it's some subset of Pauli strings that we fix. So we can either test whether you are in the set, for example, the low weight ones, this would be locality, or epsilon far from it. So it doesn't really matter which strings you take. And the result is the same, just believe me. And for example, for locality, the set would be fairly small. So like in the end, you just you now have like just the size of the set appearing, for example, in the classical post-processing time. All the rest is really the same. And well, if the property S is too large, you can do ancilla qubits, and then everything still works. That's maybe not so important. Results that didn't make it into this talk at all is just that you can also test in parallel, then you get in log M overhead, like with classical shadows. And we can also do tolerant property testing, where you're not saying that you have to be k-local or far from it, but you have to be close to k-local or far from it. So that still works. So if you now are fascinated by this topic and you want to work on this as well, then here's some open questions for you. First things, are our bounds optimal? We don't know. Is this, for example, is the scaling of epsilon to the -4 necessary, or can you do better? Can you maybe do like epsilon to the -2, epsilon to the -1? We don't know. For example, yeah, I mean, can you achieve Heisenberg scaling? Try other distance measures such as Wasserstein distances, because they are sort of more adapted to many-body stuff. And you could ask about other access models, for example, locality testing from Gibbs states, and this is actually what we are currently thinking about, but we don't know yet. And yeah, since Daniel likes Lindblad generators, you could try to do this for Lindblad generators, but we have absolutely no idea how to do it yet. Good, that's it. So that was the summary was, we talked about locality testing. We want to know whether Hamiltonian is k-local or epsilon far from it. And we found a setting in which learning is hard, but for testing, we can actually give an efficient algorithm. And if you want to know more about this, look at this paper. Thanks.
Thanks, Andreas, for the nice talk and for tailoring the open questions to my taste. Are there any other? Yeah, I guess.
Thank you. I have 2 questions. So, okay, thank you for the nice talk.
We skip that.
The first question is, in the no-go result that you have for with respect to the operator norm for coherent measurement, you are assuming an ancilla-free setting, right?
I don't think so. I think this one is actually, this one does not have to be ancilla-free, if I remember correctly.
Okay, so this implies that testing k-local Hamiltonians with respect to operator norm is hard.
Yes.
Okay, I see. Okay, thank you. And the second question is that,